I would like to now move on to quantum communication, which is the topic of today's discussion. And of course, the first question is why you should worry about it. And it's of course, I'm hoping that some of you already know the answer to why you should be worrying about this field. And why you should be worrying about it, because this actually is something which is going to prevent our current communication techniques from being jeopardized with certain advances. So, for instance, the four things that you see highlighted here, I'm sure at least the first three we are all involved in. Whether we are nowadays in with the COVID situation where I'm giving you this talk from home, it's an example where we are doing things online even more than ever, right? And so many things are going online, and so then we have to worry about how secure this transaction is. And of course, the defense is very important, and we perhaps maybe don't worry about it ourselves, but then there are people who worry about it, and we need to help them. And so all this is at being risk, of being compromised with quantum computers. And so we will, so essentially we will know how in the next few slides. And so classical cryptography is what we need to kind of counter with a quantum counterpart, and which is what is called quantum cryptography. And so these are all examples of various communication devices which we are all using, but not necessarily so secure. I mean, if the television broadcast is not meant to be secure and so on. So that is okay. But then if you want security in the communication, then what you do is essentially you have a sender and a receiver, and we actually are encrypting this message using a key, which is then being distributed. And then this key is again also available to our receiver here, who's using it to decrypt the message. So only the sender and the receiver essentially know what was intended to be sent. But then we can have an eavesdropper in the middle who might try to find out more about it and then jeopardize this communication. And so that is what we will see a little bit in detail as to how that can be somewhat prevented by using a quantum means of distributing this key. So this is what is cryptography. This I suppose you've been discussing over the last couple of weeks. So essentially you have this message, and then we have this is a simple example. So this is the, this is the number counterpart. This is the, so we basically have the ASCII, and then we have a key, and then we've done a simple operation, and then we have then undone the operation. So it's just an example to show how it works. You have private key, and then you have the public key. And so the public key is, of course, what has, the problems that we will be discussing. So the Diffie-Hellman and the RSA, these are common methods of key distribution in the public key domain. And the essential idea here is that these and others like them are based on a mathematical problem that is easy to compute but hard to crack. And that is the basis for such protocols. So now this slide is an example. It's a toy example to tell you about the difference between a hard and an easy problem. And so the thing on the left that you see is a situation which is very easy for most of us to create. But the situation on the right, only some of us take the burdens of doing this, and it is not as easy as the left one. And so that is why. How do we distinguish between the easy and the hard here? That is the time it takes to actually do this problem, right? So just making a mess with clothes, it takes very little time, but sorting them out color-wise and putting them in the cupboard and so on and so forth takes a lot more time. And so this left is an example of the multiplication problem, let's say, whereas the right is the factorization problem. So that is the idea. So amount of time it takes for you to crack a certain problem kind of tells you about what hardness class it belongs to, essentially. And so that is the problem that we will face with classical cryptography, because this hardness class could perhaps be changed with the advent of quantum. Okay, so in classical cryptography, unconditional security is not possible. For instance, as we just discussed, the RSA protocol. Now, this is based on the mathematical complexity of factoring large numbers. And so these are some numbers about how much has been done in factoring large numbers. But then typical RSA is 1024 or 4096 bits long, let's say. And Shor's algorithm, and this is Peter Shor, by the way, is an algorithm which uses quantum gates, which can perform factorization in polynomial time. So essentially something that we thought was secure because the factorization was such a hard problem need not really remain so anymore if Shor's algorithm starts kicking in and working on quantum computers. So essentially this slide summarizes the need for quantum key distribution. Okay, so computational resources, they grow very fast, and today's hard problem could be solved tomorrow using brute force attack. So we need new algorithms for classical, not new, not need, sorry. We can have new algorithms for classical computers, or we can have realization of quantum computers, which is of course definitely going to happen. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. A very important phrase here, future secure. So what I think is secure today should remain so even 10 years down the line. And so this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem, which indeed can be broken either by new algorithms on existing devices or new devices which are getting built at a very fast rate. And the most important part of this process is the key distribution itself, which is why we call it quantum key distribution. So one has to understand that in quantum cryptography, we call it quantum cryptography, but it's not quite right to call it quantum cryptography. It's basically cryptography using quantum key distribution is what we really mean mostly. So because the encryption and the decryption, those parts are still done using standard algorithms. It's the key distribution which we have now secured using quantum means, which basically does it for us in terms of getting the communication to be secure. And so quantum key distribution is kind of the quantum part of the story.